Hello, we're going to move to a different topic called as binary search trees. The catch is, the important thing is the word search trees. And first, let me motivate you on the use of binary search trees. Consider a dictionary. So you have a dictionary, right? So you all might have a dictionary. And why do we use a dictionary for? We use a dictionary to understand. So I don't know the meaning of a word. I take a dictionary and I look for that, right? Now imagine that I want to implement the dictionary in the computer. What is the good thing about a dictionary? The good thing about a dictionary is that you can search for a word very fast, right? There are, like, let's say 10,000 words in a dictionary, but you can quickly find out the word which you are interested in. It's a very big advantage there, right? Because it's the words in a dictionary are maintained in a particular order for us to identify to search for the word fast. Right, now I want to implement a dictionary in a computer. This is what we are going to do now. And how can I do that? So a dictionary, you can think of, has two parts. One is the key and the other is a value. So key is the word which you are going to search for. For example, let's say hockey. Right, that's a word we are going to search for, and the value will be, you go and look at the word hockey, you are going to see something like so it is a game, or it's a sport played with sticks, and okay, so something like this will be the value of the key hockey. Or you can have something else. You could have searched for a different word, let's say a book, right? And you see a different value. Now you want to implement this in the computer, right? And so someone, let's say, want to search for words in a computer quickly, and that's our objective. And what are we going to what is the kind of data structure we are going to use to store a dictionary? Okay, that's where it's going to be a binary search tree. We're going to use a binary search tree. And so the most important thing we are going to use is the key value, the key, because the value can be anything, right? What we are going to search for is the key. Hockey is what we are going to search for. So that's where the crucial thing is. Value could be anything, right? So that's not something we are interested in, how to manipulate the value. We are interested in how we store the key, because that's where we are going to search. Searching for key is the most important thing. And okay, let's do that. And so I'm going to, so again, we are going to have, we will see everything as integers now. And so rather than key being a hockey string like this, it might be, we'll look at some numbers. Okay, and you will soon see that, okay, you could have replaced these numbers by strings like hockey without any issue. There's one catch though, warning. A dictionary, like say for example in a Python, may not be implemented using a binary search tree. So a binary search tree, we will see a binary search tree now, and we will also see its advantages, and we'll also see its disadvantages. Okay, there are some trees which are in like more advanced trees which give better results than a binary search tree. So this is kind of the base search tree. You can go further. You can look at what are called as AVL trees, red-black trees, etc. We will just see what is an AVL tree and towards the end of this lecture. And a dictionary in, for example, Python, etc., uses um, a different concept called as hashing to for searching faster. Right. But binary search trees have certain other advantages. Okay. Now let's look at how what is a binary search tree. Again, we are going back and we are going back to trees with integers. So it's going to be a binary. First of all, binary search trees are going to be binary trees, and the but the numbers, the integers in the binary tree for the keys, right, are going to be stored in a particular order. That's the main thing. So it's going to be a binary tree, but the numbers are going to be stored in a particular order. That's the most crucial thing. So let me just give you an example for binaries. Okay. So here is the most important property of a binary search tree. Okay. Now let us say, okay, I am in a node with key value, let's say x. Okay. Okay. So node has key equal to x. Now here is the most crucial property of a binary search tree. Now every node to the left of x. Okay, so listen carefully. Every node to the left of x has key less than x, and every node to the right of x has key greater than x. Okay, so every node to left of uh, okay has key less than x. So basically I'm saying every node to the left of this particular node has key less than x, and every node to the right of x has key greater than x. So this is the most important property, and this property is preserved throughout the tree. Okay, now you go to any node in the tree, its left nodes are lesser than its key value, and its right nodes have key values greater than. Okay, this is preserved everywhere. Let's look at an example of a binary search tree. And okay, let's look at an example. Now here is a binary search tree. So this is 10, this has to be less. So I'm going to write 5. This has to be greater. What about here? This has to be 15. This can be anything greater than 20. Now let me just say why this is correct. Let's look at each and every node. 10. Okay, this node. Its left left nodes should be less than 10. Is it correct? Yeah, it's 5. All its right children has to be, so the ancestors to the right of 10, everything has to be greater than 10. 15, 20, 30, it's greater than 10. Good. Okay. Now let's come to this node, 20. Every node to the left of 20 has to be less than 20. Is it correct? Yes. 15. Every node to the right of 20 has to be greater than 20. Is it correct? Yes. Good. So this is good. Right. Let's look at another example. Again, This is another binary search tree. Look at 50. Every node to the left of 50 has to be less than 50. It's correct. Every node to the left of 7 has to be less than 7. Correct. Every node to the right of 7 has to be greater than 7. Correct. Every node to the right of 50 has to be greater than 50. That's all correct. These are all correct. Let's look at an example which is not a binary search tree. This is not a binary search tree, right? Because right of 20, it's 5, which is less than 20. This is not good. Let me, okay, this I made it into 50, so this is good. But what about if I have 70 here? This is also not good, because you have number 70 here, which is less than 70 is greater than 20, but it's on the left of 20. It's also not good. So this is therefore not a binary search tree. Okay. Now I have to argue few things, right? I have to argue why a binary it's how do you search in a binary search tree? Because I'm telling that it's easy to. So these are key values, right? So these are all keys. Sorry, these are all keys. Now what will be the value? So value can be anything. So when you create a data structure for a binary search tree, a node will contain a few things. So node contains So a node contains a key, a node contains a value, and then there will be a right pointer, a right child basically, and then there will be a left child. A node in a binary search tree will be like this, and all these numbers are keys I'm talking about, and not the value. The value could be anything here. Okay, so I'm just not talking about value because it can be anything. And you can also notice that this need not be a number, right? This could have been a string, and I can use a lexicographic ordering, right? A less than ordering and alphabetic ordering on a word. So if this was, let's say, I could have had this to be football, and this something else. So let me say this is cricket. Obviously, cricket is less than football because C is less than F in the lexicographic ordering. On the other hand, this is F, G, H. So this can be hockey, right? And what about this? This has to be greater than football and less than hockey. G, something with G, go. Okay, I'm just writing with some sports names. Right, and something greater than H. Okay, so let this be rugby. Okay, that's greater than H. So you can have so you could have had strings here, right? Okay, now this is so this is how you can have a binary search tree. Now you also saw how to I mean, if you want to create a binary search tree as a data structure, this is how it's going to be. Every node is going to have these things, right? Okay. Now I need to. We need to go further, and I will argue how to search in a binary search tree and how to insert a number into a binary search tree, and these are two important operations which we will be interested in. And finally, what else do we need? Okay. Also, I need to argue why. Why is it good? Why are binary search trees good? Why can we search faster in a binary search tree, and why it's bad? Why we would like to see an improvement on the binary search tree? These are things which we will soon see. Okay. Thank you.